Good morning, my students. Today we will continue our lesson diffraction, especially the wave aspect of light. Our objectives for this session is to recognize a wave aspect first. Second, define diffraction. Describe the diffraction pattern from a thin slit and from a circular aperture. To revise constructive and destructive superposition of waves. First, we begin with the wave aspect. In general, a wave can do many things: reflection, refraction, diffraction, interference. Reflection of water waves occurs when the water waves reach an obstacle. These are the wavefront. When reaches the obstacle, they reflected in the other way. Now, refraction when, for example, in this case, the water wave travels from deep water to shallow water, it deviates, like in this picture. In reality, the explanation of what the wave of the sea wave reaches the shore always parallel to it is interpreted by refraction. A wave is characterized by its ability to do interference. The interference will be the object of the next chapter. This is the interference at the surface of water. Our next lesson should treat the interference of light. And now a wave is characterized by its ability to do diffraction. As wave travel past an aperture, look at this picture. Wave comes parallel, and when travel past this aperture, a circular wavefront appears. This is what we call diffraction as a surface of water when travel past an aperture. A diffraction can occur when also waves travel past an obstacle or edge. Look at this picture. When sea wave reaches this edge, it deviates towards this edge, and also here when these waves reach this edge also, it deviates in this direction. Let's see this video of the diffraction of water wave. Now, after watching the video, let's recall another property of light. We have learned in grade 8 that light propagates in rectilinear path. That's what we call the rectilinear propagation of light. According to that property, if light shine the edge of an object, this light shine this part of the screen. But what really happened is that light deviate and shine a larger area on the screen. Look at this one. The light does not propagate in rectilinear path. From here to here to here, no more rectilinear path. Another experiment. If we shine an aperture, a small aperture in a screen, in a cardboard, by a parallel beam, we predict that the light on the screen take the form of the aperture and has the same size of this aperture. But what really happened, if we shine a small aperture by a parallel beam of light, that we have on the screen a circular rings, one bright, the second is dark. So alternatingly, bright and dark rings. So light as before, no more in rectilinear path. Look at this one. So light becomes here and deviate to reach a larger or point far away the distance, the direct distance what we predicted. Another experiment. So if we shine a slit by a parallel beam, we predict that according to the rectilinear propagation of light, that on the screen we should have a small point, a spotlight on the screen. But what really happens if the slit is sufficiently small? This light will deviate perpendicular to the slit, forming that what we call these things called fringes. This is a wider fringe, the central bright fringe, and the others are lateral fringes. So we will talk about these fringes later. Now questions rise. Do the light do refraction? So do the light behaves as waves? Now let's define the diffraction. What is the diffraction? The diffraction is the deviation of wave from its path without being refracted or refracted when it falls on a small aperture less than 1 mm for light, or a sharp edge. We mean by light a visible spectrum of electromagnetic waves. What we saw in this video, that light deviates when it passes through a small aperture and a small slit. So this is a characteristic of a wave. So in this case, light behaves as wave. So diffraction finally show the wave aspect of light. Now at the end of this part, we state the observation of the diffraction pattern. We see alternate bright and dark fringes on both sides of a central bright fringe. And we see that the central bright fringe is the most intense and has a width double of that of the other bright fringes. And the fringes are extended along a direction orthogonal to the slit. The slit has this direction and the pattern is perpendicular to the slit. In order to interpret the pattern of diffraction, we have to know about constructive and destructive superposition of waves. So watch the 3 videos on Google Classroom named Constructive Superposition 1, Constructive Superposition 2, Destructive Superposition, and come back here. So after watching 3 videos, let's interpret what did you see. Here a speaker emits a sinusoidal sound, and ear that hear this sound in a certain level. If we have a second source identical to the first and in phase with the first, what did the ear hear? A sound with double amplitude. So that's what we call constructive superposition. Now the same source with another source that is shifted by pi or are in opposition in phase with the second. What did the ear hear in this case? No sound. This is what we call destructive superposition. Let's know more about constructive superposition. The two sources here, and we have to try to display one of these two sources toward the ear in order to obtain again sound with double amplitude. This is the case. What is the distance traveled by the source then? This is the double amplitude. The distance traveled from this maximum to this maximum, so it is a one wavelength. The distance delta traveled by the source is one wavelength. This distance let again the ear hear a sound with double amplitude. What if we want to hear again for the next time, always approaching the source to the ear? Here again a double amplitude. What is the distance traveled from the beginning? This is a second position, and the distance traveled with double amplitude, the distance traveled is 1, 2 lambda, the delta equal to lambda. So let's call these distances d1 from the second source to the first source to the ear, d2 from the second source to the ear. The difference between them is delta. So we have the rule: if delta equals d1 minus d2 equal k lambda for k equal 1, so d1 minus d2 equal lambda for k equal 2, d1 minus d2 equal 2 lambda, where k belongs to z, it could be negative, positive. We have in this case constructive superposition, so a constructive superposition takes place. Finally, let's see the final things about destructive superposition. If we have these two sources and are in phase, the resultant is the double amplitude, and the ear hear a sound with double amplitude. If we want to shift or displace one of these two sources, the red one, toward the ear by a certain distance, like this, these two sources become in opposition of phase and we hear no sound in this case. What is the travel distance by the second source? The distance traveled, it's clear that delta, the distance, equals to lambda over 2. Now, no sound heard. If we want to again find the next position where no sound is heard by the ear, this one should replace this one. Let's see. In this case, what is the distance traveled by the second source? Delta equals lambda from here to here plus the half of lambda. So in this case, d1 from the first source to the ear distance, and from the second source to the ear is d2. Delta is the path difference between d1 and d2. So the rule says that if delta equals d1 minus d2 equals k lambda plus lambda over 2, whatever lambda belong z, positive, negative, or 0, in this case a destructive superposition takes place. Finally, the big questions for next time: do light plus light give darkness? The answer of this question and the interpretation of the phenomena of diffraction and other things will be treated next time in video number 3, inshallah.